All right, good evening, everybody. Okay, so one will consider something continue our resistor. We have done a part of a video on resistor before, and we want to continue from um where we stop at resistor. So today we want to look at the factors affecting resistance. Okay, factors affecting resistance. So there are three factors that affect resistance. Number one of the factors, we have the area. All right, we have the length of the conductor, we have this cross-sectional area, we have temperature, and those are three factors. But you can also add nature of material. Okay, now the length of a material, when the resistance of a material increases, the length also increases. That suggests that your resistance is directly proportional to the length of the object. But for the area part, when the resistance decreases, the area decreases, the area increases. When the resistance decreases, area increases. That means that your R is inversely proportional to the area. I said the factors that affect resistance, we have length, we have area, right? Then we have temperature, and we have nature of material. So when temperature resistance increases, temperature increases. That means R is directly proportional to T. But if you want to consider the first, length and the area, and I also talk about nature of material as the four factors that affect the resistance of a material. So let's work with these two. So our R is directly proportional to length, direct proportional to length, and our R is also inverse proportional to the area. If you use joint variation to combine these together, you have resistance, all right, is proportional to length, also proportional, inverse proportional to the area. Then you have R, all right, into L over what over A. All right, so you introduce a constant. Your constant is resistivity. So you have R is equal to rho L over A. All right, this is what you have. R is equal to resistivity L over A is the value of resistance in the factors. So R is equal to resistivity L over area. So that is that. Then once that has been gotten, you must understand what resistivity is. All right, if you want to make resistivity sort of formula here, so you have RA is equal to resistivity L. All right, so why you gonna have, you have what resistance multiplied by area is equal to dash over L is equal to resistivity, or resistivity is equal to RA over the length of the material. So this is what we have. All right, that being the case, now, what is resistivity? Resistivity is defined as the resistance of unit length of material of unit cross-sectional area. Okay, that's what resistance is. Resistance is defined as resistivity is defined as resistance of unit length of material of unit cross-sectional area. Okay, and the unit is ohms meter, and that's the formula on the board. This is the formula of resistivity. Okay, now what is conductivity? If this resistivity, when you talk about conductivity, what is conductivity? Conductivity is actually the reciprocal of resistivity, all right? The degree to which a conductor allows electricity or current to pass through it is what we call conductivity. And this is measured in ohms per meter, all right? Ohms per meter. Conductivity is measured in ohms per meter, all right? Resistivity is measured in ohms meter. Take note of those two things. Conductivity is in ohms per meter, resistivity is in ohms meter. Okay, so that is conductivity. Then there is a relationship between the current density J, all right, the electric field intensity, and the resistivity. Current density J, electric field intensity, and the resistivity of the material. And the formula is given by relationship. You have resistivity is equal to the electric field intensity over the current density J. Okay, so that means electric intensity is equal to rho J. All right, the multiplication of your resistivity measured in ohms meter multiplied by J, which is the current density, will give you the electric intensity in this particular term. All right, so we can use this as equation 1. Okay, let's say from this relationship, this equation 1, and this is equation 2. All right, resistivity is equal to electric intensity over current density, and current electric intensity is equal to resistivity multiplied by the current density J in that manner. So I said conductivity is the reciprocal of resistivity. The symbol of conductivity is sigma, which is 1 over resistivity rho. All right, sigma is 1 over rho. Okay, so we'll get back all of that. How was ohms per meter gotten? We can find it. Resistivity is equal to RA over L. So your resistance is in ohms. So you have ohms multiplied by what is area measured in meter square over what is length. Length is in meter. So meter cancel 1 meter here. Then resistivity is equal to ohms. Alright, so we have meter square over meter. Meter has gone. Then resistivity is now in ohms meter. Okay, that is how resistivity is measured in ohms meter. Then when you talk about sigma, your conductivity, which is sigma, you have sigma is equal to, so you now have 1 over what? 1 over ohms meter, which is sigma is equal to ohms meter raised to power minus 1. That is how the sigma is measured. And I've given the value. So sigma is equal to 1 over resistivity. That is conductivity. And I said that is defined as the measure or the extent to which a material allows current to flow through it. Okay, so that's conductivity, and resistivity is the resistance of a unit length of material of unit cross-sectional area, so in ohms meter. So that is that. So from that formula on the board, E is equal to PJ rho J, which is electric intensity is equal to rho is the resistivity multiplied by J is the current density. Okay, current density. I've spoken about it in one of the video. I thought about current density in one of the videos. So now let us move on to get our equation 6. Now, anywhere we see resistivity, all right, we can rewrite it as 1 over sigma. Okay, if that is the case, I can now write E is equal to, when my resistivity is equal to 1 over sigma, from sigma is equal to 1 over resistivity, so I can now write 1 over sigma multiplied by current density. Then I have E is equal to J over sigma. All right. So if electric intensity is equal to J over sigma, then what is the value of J? Then we have what? Electric intensity multiplied by the conductivity is equal to J, or what? Or J is equal to what? Electric field intensity, or sigma conductivity multiplied by what? Electric field intensity. You can use that down as equation 3. Current density is equal to conductivity. This sigma is conductivity multiplied by electric what? Electric field intensity. Okay, so that is how to prove the equation down. Then that is equation number 3. Okay, so those are the three relationship between your resistivity and conductivity, your resistivity, electric field intensity, and the current density of the material. So, and that's how to prove your resistivity formula, and you can apply them in equation anytime, any day. So now, what are the factors? Okay, of course, there are things we need to take note of in these two values. When your resistance is proportional to area and inverse to length and inverse to the area, there are instances we need to take note of. For instance, if your R is equal to length, R is equal to length, then your R is equal to KL. Alright, if it's KL, what is K? K is equal to, you can say R over L is equal to K. That means your R1 over L1 is equal to R2 over what? Over L2. Okay, you can use this formula when you're having two different resistors, and maybe you're given one length and you're looking for the other length. But for the area, what are you going to be having? You have R is equivalent to 1 over area, then you have R is equal to K over area. So area is coming to this side, then you have RA is equal to K. So you can know this formula, write this formula down, note it. Okay, so what do you have? You have what? R1A1 is equal to what? R2 what? A2 is equal to K. That means at the end, we are going to be having R1 over R2, R1 over R2 is equal to A2 over A1. Alright, A2 over A1. Know this formula too. Alright, when you're having two resistors, maybe one area and you're looking for the second area in meter square. If it's given in centimeter, you convert. Alright, so that's how to go about all of those things. Okay, so then lastly, let me talk about the effect of temperature on substance. The metallic conductor, alright, we have the effect of temperature on metallic conductor. Resistance increase as the temperature increases. We have effect of temperature on insulator. Alright, at metallic conductor, when resistance increase, the effect of temperature on metallic conductor is that when resistance increase, temperature increases. Okay, but the effect of temperature on insulator is that when resistance decrease, the temperature increase. Then on semiconductor, when resistance decrease, the temperature of the semiconductor increase. Resistance decrease, alright, the temperature of the semiconductor increase. After the one metallic conductor, insulator, then this semiconductor. Then for electrolyte, when resistance of an electrolyte decreases, the temperature increases. Okay, then for gases, at high temperature and low pressure, resistance of the gases, alright, decreases. Okay, and there is a graph, alright, for that. Okay, so I'll just draw the graph there. We'll take one question on that, and that is for this video. Alright, so we have a graph like this on the effect of temperature on the substance. I've mentioned for 5 different substances for metallic conductor, which is increase in temperature, increase resistance and increase in temperature. Okay, then we have, I mentioned insulator, semiconductor, electrolytes, and gases. So this is what we have. So we have from R. So let us say this R and this R from the final value of the resistance to the initial value R naught. Okay, and let us say this theta. Okay, we can have that as the graph. Then this one will give us the slope, which is R naught theta. Slope R naught theta. Okay, so that's the slope. So now let's move now. All right, or we can use alpha, any of the two. R naught alpha is the slope. We know what slope is. All right, you have the change in value in the vertical axis, then over the change in value at the horizontal axis. Okay, so if this final theta, your slope is now going to be n. All right, or yeah, n is equal to, that is change in resistance over the change in value of the angle. Okay, so that's what we're going to be having, resistance and an angle. So that is that. Then quickly question. So the question goes thus. We want to take one question on resistivity. So the resistance of a wire of length 50 centimeter. So they gave length of the wire to be 50 centimeter, which is converted to meter. This question, all right, is going to be, if you convert it to meter, 50 centimeter to meter will give you 0.5 meter. Okay, then quickly they said, and the diameter is 0.4 millimeter. So diameter is going to be 0.4 millimeter. 0.4 millimeter, you convert millimeter by dividing by 1000. Then it's found to be 6 ohms. So resistance is given to be 6 ohms. So you have 6 ohms at that particular point. Then what else was given? That is all the parameter that's given. Length 0.5, diameter 0.4. Then the noun said calculate the resistivity and the conductivity of the material. So to calculate for resistivity, what is the formula for resistivity? You have what? Resistivity, okay, is equal to what? RL. Resistivity is equal to what? RL over what? Over A. But in this A, they gave a diameter. So what is your A? Your A is pi R squared. And what is R? R is equal to diameter over 2. So at the end, you have your value of A to B. Anywhere you see R, you have pi. Your value of R is now diameter over 2. Because of the square, you put square there. Then area is equal to pi diameter squared over 4. So anywhere you see the value of resistivity, resistivity can also be Rn over, anywhere you see area is now pi diameter squared over 4. So 4 will go up. You have resistivity is equal to 4 rho L over 4 rho L over pi diameter squared. Alright, and diameter is reduced over 2. So take note, you can use this formula to calculate for that. So 4 multiplied by your resistivity, your resistance rather, resistance. Resistance is 0.5, length 0.5 rather, resistance is 6, alright, pi is 22 by 3.142, then diameter squared, that is 0.4 divided by 1000, a meter, then you put a square in that place, okay, then you find it. So once you are done with that resistivity, 1 divided by resistivity will give you the conductivity. So the value, if you solve down, the value of resistivity is given to be 1.5 times 10 raised to power minus 6 ohms meter, okay, solve down. Resistivity is 1.5 times 10 raised to power minus 6 ohms meter. That's what we have when you calculate down. Then you have your conductivity to be 1 over resistivity. Then when you calculate down, you have a value of 6.67 times 10 raised to power 5. Okay, 6.67 times 10 raised to power 5. That is ohms per meter or per ohms per meter. Okay, per ohms per meter is the SI unit. Per ohms and per meter. Okay, so that is what you have. That's how to calculate for all of those concepts. Okay, thanks for watching. All right, and God bless you. All right, so like I said, if there's any question, you can reach out to me on my WhatsApp 09074564847 and let me know the issues you're having. All right, so we'll continue the class, and any question, any video you want me to do, maybe you have a topic you want me to do one video on, just send it to me on WhatsApp. All right, thanks for watching and God bless you.